Let us start today's video by recalling that we have come across one result, namely Theorem 2.1, which gives us a necessary and sufficient condition for a first order equation to be exact. So today we are going to use this result to see some examples. So let's start with this example 2.3. And here we have this differential equation y square dx plus 2xy dy equal to 0. So you know that it's in the form m dx plus n dy equal to 0. There are two forms in which you can express a first order equation. This is the differential form. So here m is y square and n is 2xy. M and n both are functions of two variables x and y. So what do we have to do to check that this equation is exact? We differentiate m partially with respect to y and n partially with respect to x and see if these partial derivatives match. And wherever they match, this equation will be exact according to Theorem 2.1. Luckily, these two partial derivatives match everywhere, because if you differentiate this partially with respect to y, what will you get? Because it has only y, x is not there, so it will be ordinary derivative 2y. So that way this is equal to 2y. And if you differentiate this partially with respect to x, y will be considered constant. So here also you are getting 2y. So they match for all x comma y belonging to the two-dimensional plane. And that is why the differential equation is exact in any rectangular domain. Let us also recall that in the original statement of Theorem 2.1, we considered rectangular domains, because we are going to use that thing here to claim exactness or to conclude exactness. That's why we are just saying that in any rectangular domain this is the case. So the equation is also exact there. And next, actually if you recall, these are examples we have already seen. In fact, before stating Theorem 2.1, and then only we asked should we come up with some result that will help us to say that an equation is exact. So that's how the theorem came. So this second equation, you may remember when we discussed these two examples, is not exact, and it is y dx plus 2x dy equal to 0. In this case, m is y and n is 2x. Del m del y is the constant 1 anywhere in the plane. For any x comma y in the plane, this is 1, whereas del n del x is 2. So they are never equal, and that is why this is this inequality, that these two partial derivatives are not equal, this inequality is true everywhere in the plane. So in particular in any rectangular domain also this is true, so it will not be exact. So let's continue from that side. Okay, so we write that the differential, the second one is not exact in any rectangular domain be in the plane. Next we have this example where the equation is a little more complicated. So the equation is this: 2x sin y plus y cube e to the power x times dx plus x square cos y plus 3y square e to the power x dy equal to 0. So that means in this case, this is m 2x sin y plus y cube e to the power x, and the function n is this one, x square cos y plus 3y square e to the power x. And here also you have the condition for exactness true. Okay. So if you differentiate, let's just see it carefully. You have to differentiate m partially with respect to y. So if you do so, if you differentiate the first term here, because you are differentiating with respect to y, so x will be considered constant. So that means this will be 2x cos y, because sin y will become cos y when differentiated with respect to y. What will happen here? E to the power x will be considered constant, and y cube will become 3y square. Where am I showing 3y square? Here, 3y square e to the power x. On the other hand, if you differentiate n with respect to x, then y will be considered constant. So from this term you are going to get 2x cos y. Because y is constant, cos y is also constant. So that way you actually are again getting 2x cos y. And from this term, this won't really change. Y is considered constant and we are differentiating partially with respect to x. The exponential function when differentiated, it doesn't change. So that way you get this. And this also happens just like the first differential equation of the previous example throughout the plane. So this equation will also be exact in any rectangular domain in the plane. So let's continue. Okay, so this differential equation is also exact in any rectangular domain D in the plane. Now after this there is a caution given by the author. Let's see what that thing is. The author asks us to be careful with this test. Before applying this test for exactness, we should make sure that the differential equation really is in the standard form. Then only the test is applicable and will not be applicable to a first order equation of this type but which is not exactly in standard form. For example, if you have an equation which looks like this, you still have m dx and you still have n dy, then to this m and this n, it will not be applied. I mean, it should not be applied because it's not applicable. But if you rearrange things and bring this equation into standard form, then on that rearranged equation it can be applied, which means that you have to take this term to that side, or maybe you can take this entire thing to this side. So the equation to which the test will be applicable will be m dx minus n dy in this case. And there also you should not consider m and n as that m and n. I mean, m of course you can take m as m itself, but in place of n you have to choose minus n. Then only it will make sense. Next, we have the solution of exact differential equations. What we have seen so far is a test for seeing whether a given first order differential equation is exact or not. So say you apply the test and you find that an equation is exact in some domain. What do you do then? Next comes the question of solving it. So for that, let's consider this equation which is known to be exact in some rectangular domain D in R2, that means in the plane. Then by the definition of exactness, not by theorem 2.1, okay, you recall the original definition of exactness. That definition tells that such an equation is defined to be exact if there exists a function f from that domain into R, which means that f also, just like m and n, is a function of two variables and f has d as its domain, such that the first partial derivatives of f with respect to both these variables exist and are continuous in d, and del f del x is equal to m and del f del y is equal to n for all x comma y belonging to d. Okay, so this is just the definition of exactness. But then if this is the case, we can write this in place of m and this in place of n. What will then happen? Let's see. So then the differential equation becomes this. We have replaced m by del f del x and n by del f del y. Maybe I should have kept on writing for all x comma y belonging to the domain D, because in that domain only those equalities are true. But let's assume that that thing is in the background. And then you notice that this left hand side is the total differential of the function f. So that way you get the fact that df is 0. So f then has to be constant. So that is how you get a relation involving x and y which is devoid of derivatives, and that is a solution of your original differential equation, and here c is an arbitrary constant. Okay, fine. So this is how we can solve an exact differential equation. But of course the question remains how to actually find f. If we were given an equation m dx plus m dy is is equal to 0. Exactness simply tells you that an f exists, but what is f? What exactly is f for a given equation? So you go back to you recall the proof of theorem 2.1, where actually we formulated this test for exactness. That proof was fairly long and complicated, and towards the end of the proof you may remember that we derived a complicated expression for f. We proved that f should equal an expression involving many integrals, which of course has those functions m and n. At that time I made a remark that we do not have to remember that expression to actually solve a concrete first order exact differential equation. But then what do we do? Well, every time we get such an equation, we are essentially going to prove that, go through that proof again. It sounds extremely scary at first, but you will see that when you have a concrete exact equation, not a general one, not m dx plus n dy where m and n are general, but a concrete one, then finding f, the way we did the proof, really becomes extremely easy and intuitive. That is one way of doing it. There is another way also, it is called the method of grouping. That we won't discuss today, we will discuss it in the next differential equation video. Today, however, next let us consider one example where we are actually going to do it, and let's do that next. Okay, so let's next consider this example 2.5. It's in the form of a question. We have been asked to solve this differential equation. It's in that form, m dx plus n dy equal to 0. M is 3x square plus 4xy and n is 2x square plus 2y. Now next, naturally we go for the test for exactness. So we calculate the partial derivative of m with respect to y. So what will you get from this expression? Because we are differentiating partially with respect to y, the first term contributes 0. What happens to the second one? 4 and x are constant, and here you have y. So the derivative, partial derivative will be 4x. What will happen if you differentiate n partially with respect to x? Then you get 4x from this term, and this term contributes 0. So again you are getting 4x, and this equality is true for all x comma y belonging to the plane R2. And that is why our differential equation really is exact in any rectangular domain D in the plane. So next comes the real part. Now that we know that our equation is exact, we know that a function of this form f from D to R will exist, which satisfies the usual conditions that first partial derivatives exist and are continuous. Those things are there. But the main thing is that del f del x will be equal to m and del f del y is equal to n. That means these things. Now you recall the proof. What did you do in the proof at this stage? You naturally did what? You did integration. Okay, actually you integrated both sides of this first expression partially with respect to x. So here also we are going to do that, and then an arbitrary function of y will come. Recall that part, phi of y. So those things will now come. So if you integrate both sides of this equation partially with respect to x, you will get f on the left hand side. The right hand side, 3x square will become x cube, because x square when integrated becomes x cube divided by 3. And integrating x, you will get x square divided by 2. So in place of 4xy, you are going to get 2x square y plus phi of y, where phi is some function of y only. Next, what do? We have to somehow use this equation also. Again you recall the proof. What did we do after this? We differentiated both sides of this equation partially with respect to y, so that we can incorporate this partial derivative. So what will that give us next? So next we do just that. We use this equality So that way we have 2x square plus y equal to del f del y. But this del f del y this time can also be calculated using this equality. So if you differentiate partially this expression, this right hand side with respect to y, the first term will contribute 0 because there is no y. This will turn into 2x square plus this becomes the ordinary derivative of phi with respect to y. So you see that 2x square and 2x square cancel each other from both sides. So that way you get d phi dy equal to 2y. Now this is a very simple differential equation itself, which if you solve, I mean you just have to integrate both sides. You get phi equal to y square plus c naught, where c naught is an arbitrary constant. You may also remember that while doing our actual proof of theorem 2.1, I did not write, in fact the author himself did not write any plus constant. But say, just for the sake of our habit that we have picked up from integral calculus, when you integrate we add plus constant because you are writing an antiderivative, and by integral we mean indefinite integral. So we will see what happens to this constant afterwards. So now what will you do? You will put this here, alright. So that will give you an f. An f means actually it gives you a family of f because this constant can be changed. So let's do that and see what we get. So using this expression for phi, f turns out to be this, x cube plus 2x square y plus y square plus c naught. So that's it. You have found f. Do you see how easy it is? The proof was complicated because it was general. There you worked with general functions. That's why it was complicated. But anyway, so finding only f is not enough. I mean, you have done whatever you had to do and we are almost there, but this is not the solution. Don't stop here. The solution is f equal to some arbitrary constant. So let's call that constant c1, or this is equal to c1. This is a solution to our differential equation. Now it seems like we have got two arbitrary constants, but actually these two arbitrary constants are not independent of each other. I mean, well, you can take anything in place of c0 and you can take anything in place of c1. So that way you can think of them as independent constants, but ultimately they can be combined to give one constant. So that's what we write next. So writing c1 minus c0 as c, because if you subtract c0 from both sides, on the right side you will get c1 minus c0 and the left side will not have c0 anymore. You get this one parameter family of solutions to the differential equation. X cube plus 2x square y plus y square equal to c, where c is the parameter or an arbitrary constant actually. And finally, the author makes a remark about this entire thing. We have used y square plus c naught as our phi. That means we are writing a family of such functions phi, not a single phi actually. But if you write a single phi, for example, if you take c naught equal to 0, you are then going to write y square only. And say with that you go ahead and you do whatever you have to do here, and finally you use one arbitrary constant c, you are going to get exactly the same family of functions. And I want to make one remark here. Do you recall that when we discussed about solutions of differential equations, there we went through a number of things. In what sense are we going to get these solutions? We discussed quite a few things. We said that it's a luxury in differential equations to get exact solutions. Now we are getting it, but here also there are two forms in which you can get the solution. One of them is as an explicit function where you have the dependent variable as a function of the independent variable. The dependent one is y and the independent is x. So y equal to log x plus 3x square something. Okay, so this side is entirely an expression involving x. So that's an explicit solution. But you may also get an implicit solution. We actually did some exercises on this also, if you remember. This is an implicit solution. Here you don't instantly get y as a function of x, but you have got a relation between x and y in the form of this equation, and using this relation you can define one, possibly more than one explicit solutions which are solutions to the original differential equation. At least one explicit solution is hidden here. Okay, and with that, let's just end this video and let's see tomorrow whatever we have. So that will be all for today. See you tomorrow with something new. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.